Today we're going to look at topic 4.1, which deals with oscillations, or things that vibrate or move back and forth with a regular interval. This is going to lead us into our discussion on waves and wave behaviors. So let's start by talking about some examples of oscillations. Some of these you're probably familiar with, you've seen. Pendulums, you used a pendulum when you investigated the mass of the Earth, actually in the last unit. You'll remember that the pendulum is simply a mass hanging from a string of some length that moves back and forth due to the restoring force of gravity and the tension in the string. And as you watch it, it moves back and forth again at a regular interval. A specific example of pendulums are swings. I'm sure we've all sat on a swing and swung back and forth at some point. Tuning forks are another good example of oscillations. And again, here we have a material that's vibrating back and forth. In this case, you have your tuning fork, and it's the tines of the tuning fork that are actually vibrating back and forth at some regular interval, and the frequency with which the tuning fork vibrates back and forth is the frequency of the sound that's generated. Instrument reeds are another good example. If you play a sax or a clarinet, you'll know that you have that little wooden reed that you attach to the mouthpiece, and as you blow across it, that reed vibrates. Quartz watches actually have little crystals in them that oscillate, that vibrate back and forth at a regular interval, which is what helps keep the wristwatch running at a constant rate, keeping accurate time. And then on the sun and in antennas and things like that, and we'll talk more about this a little bit later on in the year, we actually have charged particles, electrons primarily, that oscillate back and forth, that move back and forth, and in their moving back and forth, they generate electromagnetic waves. Now we have a lot of different types of vibrations. Ones that we are going to primarily focus on are what we call isochronous. And you might recognize the prefix iso, which means the same, and then chronous is relating to time. So same, time. And then obviously oscillations are things that oscillate back and forth. And so isochronous oscillations are ones that take the same amount of time for each cycle. So the period of the cycle is the same for each period regardless. Our simple pendulums that we used a few weeks ago are good examples of this. And things like grandfather clocks, right? They use a simple pendulum, right? And they have these big pendulums hanging down here, and they go back and forth, and that regular repeating isochronous swinging is what keeps the grandfather clock in sync or in time, keeping accurate time. And as we just mentioned on the previous slide, in a watch they use quartz crystals, but it's the same idea. It's this regular interval for the oscillations, and that helps to keep the timing object in time. As we work through, and these are going to be important through this whole unit, not just for talking about oscillations, but in waves in general, a couple terms that are going to be important. A cycle is one complete oscillation, or one complete wave, or one complete revolution if we're talking about a circle. So if we're talking about like our pendulum, we start here, and that pendulum swings to the far peak, and then it swings back to the starting point. That's one full oscillation. Circles, it's one full circle. When we're talking about waves, it's going to be one full wavelength. The equilibrium position is basically the rest position. It's where would that object be if it wasn't being disturbed. And we'll come back to our pendulum just because it's convenient and we're familiar with it. But if we have our pendulum, the pendulum rest position is going to be just hanging straight down. In order to get the pendulum moving, we have to exert some force. We have to pull it away from that equilibrium position and then allow it to swing back and forth. The amplitude, which we're going to show with an x sub 0, is the maximum displacement. Okay, so it's the maximum displacement of the object. It's how high does it go from that equilibrium position, and it's always measured from the equilibrium position. Now, as we watch our pendulum kind of oscillate back and forth, back and forth, back and forth, the displacement from that equilibrium position at any given time is going to change on a regular basis, right? At any given point, it has a different actual displacement, and at some points as it passes through the equilibrium position, it's even going to be 0. But the amplitude is that maximum displacement from equilibrium. Okay. Then our time measures our period, which we symbolize with a capital T. And so again, it's a time we're measuring. It's just a time for one complete cycle. So we still use T. We just use the capital T to kind of indicate that we're talking specifically about oscillations, waves, cycles, and it's the time to complete one complete cycle. Then we have the frequency, and the frequency is the actual number of complete cycles per second. So still related to time, but slightly different way of looking at it here. Time is the amount of time for one cycle. Frequency is the number of cycles per unit time. Our basic unit for frequency is the hertz, and so we symbolize that with an Hz. And if you're familiar with radio and radio frequencies, you may recognize that. We have megahertz and gigahertz, and again, those are all just components. It's the same thing. Mega, of course, then would be 10 to the 6th hertz. And we're measuring, in that case, the frequency of the wave. And before we get into this particular diagram, I guess I didn't have it in here, the relationship between those two, the relationship between period and frequency, so T and F. You might have recognized that they're going to be inverse. So the period is equal to 1 over the frequency, and the frequency then is equal to 1 over the period. And so if we have a pendulum, again our pendulum, and let's draw our pendulum, and we say our pendulum takes 2 seconds to go here and back. So the period is 2 seconds. Okay, time it takes for that to happen. The frequency is going to be 1 over 2, or 0.5. And that makes sense because in 1 second, the frequency is the number of cycles per second. And so after 1 second, it's going to have gotten to this point here, which is halfway through the cycle. And so it travels a half a cycle per second, which is 0.5 hertz. Remember, hertz are cycles per second. Okay, now to come down to this diagram that we have down here at the bottom. just to identify a couple components of this relative to what we were just talking about. So this is a graph of displacement versus time. When we graph waves, we can also graph displacement versus position. You might remember that from last year in CP if you took it, but we'll get into that later on. This line up here where it says A, this is the amplitude. That is the maximum displacement from equilibrium. Now, what you'll notice then, though, is that on the other side we have negative A. Okay, the magnitude, the absolute magnitude of those two values is the same. So basically what we're saying is it moves the same distance from equilibrium in both positions. So it just changes in different directions, but the magnitude is the same. And then if we look at any given point along here, whether it's here, here, or here, the displacement at any given time changes, and we don't have to get into the math of this really too deeply, but if you've done any work with sine curves and sine cosine equations, you'll understand that the displacement is a function of time as it relates to the frequency of the wave. And so after some amount of time, t, that's our period, and we're back to where we started. So after one period, the displacement is back to wherever it started, wherever we started timing from. So we have our amplitude, we have our displacement, we have our period on here. And then from this, if we know what this time is, we can then calculate frequency as well. Okay. Now, just to add this in, because we just finished talking about circular motion and looking at it in terms of radians, we also have a value that we call angular frequency, and you'll notice that the symbol for angular frequency is the same as what we used for angular velocity. It's that omega, a little curly W. And again, it's similar. It's found by multiplying the actual frequency by 2 pi. And this then gives us the number of cycles per second in radians. And so basically we're looking at radians per second. Because if we consider our units, let's say we have a frequency of 1 cycle per second. That cycle, this thing right here, isn't really, it's just like a placeholder. It could be cycles, it could be waves, it could be anything, but it's not really an inherent part of the unit. Really, it's just 1 over s. So when we multiply that by 2 pi radians, we get, in this case, 2 pi radians per second. Okay, so if we have a frequency of 1 cycle per second, that means we have 1 complete oscillation or 1 complete wave per second, and we know that 2 pi, we draw a lot of these parallels, but 2 pi is 1 full circle, or it's 1 complete wave, and that's ultimately what we're talking about here. So we see this, and we see radians in circular motion. Also, we're talking about oscillations and simple harmonic motion and waves and vibrations. Okay. Now, simple harmonic motion, because ultimately when we talk about oscillations, when we talk about this isochronous oscillations, we're really talking about simple harmonic motion, which we will occasionally see just shorthanded as SHM, and you'll see that down here we have SHM, just because it's easier to write. This occurs when we have an object or system that oscillates back and forth at a regular interval. So what's that regular interval called? That's an isochronous interval. Okay, same time, regular interval. Now, what makes this special or unique or whatever is that we have a lot of things stay regular, and we can draw a lot of conclusions. We can draw a lot of mathematical relationships, and one of those is related to the acceleration. And if we'll get into this a little bit more depth here in a second, but ultimately the acceleration of the object is always towards the equilibrium position. All right, so we'll come back to our pendulum. Here's our equilibrium position. If the pendulum is moving in this direction, as it passes through equilibrium, it's slowing down, which tells us the acceleration is in the opposite direction. Once it reaches that maximum amplitude and it starts to accelerate back towards the equilibrium position. This then tells us, and again, referring back to previous units and our complete understanding of Newton's second law, if our acceleration is in one direction, that means the net force has to be in that same direction. So the net force and the acceleration are always in the same direction. In this case, that force that we're talking about is called a restoring force. Now, similar to when we talked about circular motion, how the centripetal force is not a new or unique force, it is simply a specific application of whatever the forces already are. Restoring force is the same way. It's the net force in a simple harmonic situation. And so it could be gravity, it could be tension, it could be elastic force, it could be any variation or sum of a combination of forces. Now, what's unique to simple harmonic motion is that that force is proportional to the displacement of the object from equilibrium. So, for an object to be in equilibrium, there has to be a restoring force. But more specifically, we have two particular conditions for an object to be in simple harmonic motion. And this is one of those things that pops up that you're going to be asked specifically, probably on the test for this unit, probably on the IB exam. What are the conditions necessary for an object to be in simple harmonic motion? And those two conditions are: the magnitude of the force is proportional to the displacement of the object. Okay, so there's number one. And what that means is that the greater the displacement, the greater the force. The smaller the displacement, the smaller the force. And then part two is the direction of the force is always towards the equilibrium position. Okay, so it's always back towards the equilibrium position. And then kind of beyond that, because these two pieces are true for the force, for the net force, then the same must be true for the acceleration, because the force, the acceleration is proportional to the net force. And if the acceleration is proportional to the net force, then it's proportional to negative x, where x is our displacement from equilibrium. And it's a negative because it's in the opposite direction. Okay, opposite direction. That says direction. Again, we'll come back to our pendulum because it's a nice, easy example. We'll talk about some more examples in class and how these apply. But for our pendulum, as we're hopefully painfully aware at this point, the net forces on a pendulum are the gravitational force that acts straight down at all times and the force of tension that acts along the string. The net force then is the combination of those two. When we talked about circular motion, it was towards the center of this circle as it traveled around and around and around. Here it's a pendulum, so there's no circular, well, technically there is circular motion. It's around this larger circle. But the net force in this case is actually in this direction, right? And so it's pulling it down, and so we have, as it's moving from left to right, the force is to the right, and so the object accelerates to the right. Once it gets past this equilibrium position, the direction of the net force changes, and so our velocity is at its maximum as it passes through the equilibrium position. As soon as it passes through, the acceleration starts to go in the opposite direction because the net force is in the opposite direction. It slows down until it reaches a velocity of 0 here, at which point it then starts to speed up back in the other direction. As we go from equilibrium to this maximum amplitude, the magnitude of the velocity is constantly getting larger, so the magnitude of the acceleration is constantly getting larger. And then as we move back towards the equilibrium position, the magnitude of the net force is getting smaller, so the magnitude of the acceleration is getting smaller. If we were to kind of get to the extreme point, if we were to pull it all the way up here, okay, essentially the force of tension at this point is 0. So the net force is equal to the force of gravity. And as it falls through here, the force of gravity stays the same. The magnitude of tension increases, and the net force then decreases. Thinking about it at equilibrium, the forces are exactly opposite. And so we have force of gravity, and we have the force of tension. And yes, there is a net force. It is that centripetal force that is the difference between tension and gravity. But if we look at the force in the direction of motion that would affect the speed of the pendulum bob, the force in the direction of motion is 0, so there's not going to be any change in speed at this case. And that's that's an important piece where we differentiate here between uniform circular motion and something like this with our pendulum bob, because in uniform circular motion, as we swing it around, the speed we're assuming stays the same. In simple harmonic motion, especially with our pendulum, the speed of the object is not uniform. It's speeding up as it moves towards the equilibrium position. It's slowing down as it moves away from the equilibrium position. So that's a key difference here. When we have a spring, it's similar. It's just the forces that we're dealing with are different. If we have a mass on a spring oscillating up and down, the upward force is the force of tension in the spring. The downward force is the force of gravity. And as we've talked about when we talked about Hooke's law, we know that the more that a spring is compressed or stretched from its equilibrium position, the greater the restoring force, the greater the force, the elastic force, F equals negative kx. Maybe we'll remember that. And so if we look over here, as our spring is pulled down more, the elastic force increases, and so there's a net upward force because the gravitational force stays the same. As it moves up, and we get to this point, as it passes through equilibrium, the elastic force and the gravitational force are equal. And then as it moves above equilibrium, again, for our springs, remember that the gravitational force doesn't change. So as we move above this equilibrium position, gravity stays the same, elastic force decreases, so now gravity becomes the larger force, and so the net force on this is down. If we look at these graphically, if we were to graph the position, and here we're just assuming we start the graph at the maximum displacement. It doesn't ultimately matter, but we're starting here at the maximum displacement, which is the amplitude, and here's kind of what's going on over here. It's a spring just oscillating up and down. So displacement, it's going to fall through our O here. This is equilibrium. Momentum carries it through equilibrium. It reaches the far side, and then it starts to move back and up and down, up and down, up and down. So at our 0 points, the displacement is 0. It's at the equilibrium. At our points where we have A, it's at the maximum displacement above equilibrium, and then at B, it's at the maximum displacement below equilibrium. This is the actual equation. So the displacement x at any given point is equal to the amplitude x sub 0 times the cosine of omega, the angular frequency, times the time. So we can see at any given time we can find what the actual displacement is. You don't need to know this equation for IB. They've since removed that, but I think it's helpful to understand that, to know that. Then if we look at the velocity graph, you should hopefully notice, and we'll look at them on top of each other here in a second, the velocity graph for the exact same motion is slightly different. At the maximum displacement, A, remember, is where we have maximum displacement, so that's this here. At that instant, the velocity is 0, and so we see that here, the velocity is 0. As the object falls down through equilibrium, when it reaches equilibrium, it's moving at its maximum speed. Now in this case, it's falling down, so the velocity is negative. As it passes through equilibrium, it immediately starts to slow down until it reaches B, which is that maximum negative displacement. Again, at the amplitude, our speed is 0, and then it starts to speed up in the opposite direction. Now it's moving back upward, and in this case then we have, as it passes through the equilibrium position, we have the maximum speed but in the positive direction. Okay, so what this looks like together is our graphs, our velocity graph is what we call phase shifted. Okay, it's phase shifted to the left by a factor of pi over 2, which is simply a quarter of a period. This pi over 2 is what we call the phase difference of the two graphs. It's the shift, it's the difference between the two. So here's our displacement, and you can see at some time here, let's use a different color, the velocity is at its max when our displacement is at 0. The velocity is at its minimum, or at 0, when the displacement is at its max. And so that gives us that pi over 2 shift. Okay, that's right here. It's pi over 2. Okay. Then we have acceleration. And again, remember the acceleration is proportional to the displacement. And so when we have our maximum positive displacement, we have our maximum negative force and our maximum negative acceleration. As the object passes through equilibrium, the net force on the object is 0 because the displacement is 0. Again, here's our equation. And actually, if you remember, our velocity was v equals negative v0 sine omega t. And if you consider what the difference here, we have sine with the position, it was cosine. Right, and what's the shift between sine and cosine? It's pi over 2, right? Now here, we're back to cosine, but it's negative. And when we have negative cosine, that gives us a shift of 180, or pi. And so our acceleration is shifted by 180 degrees from our displacement, and this is, again, back to that idea that acceleration is proportional to negative x. Okay, because acceleration is proportional to, or excuse me, because force is proportional to negative x, and we know that force is proportional to acceleration, or vice versa. Now, if we put it all together, we see something like this. So our displacement is, whoops, I don't want to do that. Our displacement is here in yellow. Our velocity is this one here in purple. And then our acceleration is this one in red. And so when you look at them all three together, besides this highlighter making it way more clunky than it needs to be, we can see how those graphs all compare. At the maximum positive displacement, that color's terrible. Let's use, how about that? Let's do that color. Okay. So at this maximum positive displacement, we have 0 velocity because it's stopped. The acceleration is at its maximum, but it's in the opposite direction. As the displacement passes through equilibrium, the net force is 0, and so the acceleration is 0, but the velocity is at its maximum. As it moves back down towards the maximum displacement on the other side, the acceleration is at its maximum in the opposite direction, and again, our velocity drops to 0. And so you can see this how these three variables cycle through as we move through time. Now, beyond the kinematics piece of this, again, it's just kind of this idea that the acceleration is equal to or is proportional to the displacement. Again, this omega, this isn't an equation that you are going to have to use, but it's good to recognize because this really is the fundamental relationship in simple harmonic motion. It's what they call the defining equation. The acceleration is equal to negative omega squared, where remember omega squared is the angular frequency times the displacement. Okay, and from there, if we got through and we got into calculus and all kinds of other fun stuff, we could see where that ultimately comes from and where it leads to. We're not going to worry about that today. So, as I was saying, beyond the kinematics, we should also understand the energy relationships here, because as you probably noticed, we have a change in position. We also have a change in velocity, right? We have a change in velocity. I didn't draw that well, but if we have a change in position, we have a change in velocity. We also then should recognize that there's going to be changes in the energy involved. And in this simple harmonic motion, our energy is going to be switching back and forth between kinetic and potential. And we should hopefully recognize that the kinetic energy max, or the maximum kinetic energy, occurs when the velocity is at its max, which occurs when displacement is equal to 0. And so if this dotted line, which we'll make red here, is our kinetic energy, it's entirely kinetic when it passes through equilibrium. It's entirely kinetic when it passes through equilibrium. Because the velocity is at its maximum, potential energy is dropped to 0. When it's at its maximum potential, or maximum displacement, the velocity has dropped to 0, so the kinetic energy has to be 0. Right? When the velocity drops to 0 here, and it's 0 here, we know that Ke equals 1/2 mv squared. So if V equals 0, kinetic energy equals 0 joules. meters per second, and joules, units on everything. So it has to go somewhere. It goes into potential energy. Our potential energy is at its max when the displacement is equal to the amplitude, when it's at its maximum displacement. Okay, when it's at its maximum displacement, and then it's at its minimum as it moves through equilibrium, because all the energy is kinetic. Now, one thing to notice with our energy is it's all positive, right? It's this oscillation between positive and negative, whereas our displacements, we oscillated across from positive to negative. Again, remembering that displacement, velocity, and acceleration are all vector quantities. Energy is a scalar quantity, and we're not losing energy here. It's simply being transferred from one type to another, kinetic to potential, potential to kinetic. And so we don't ever have negative energy. It always stays positive, and we just see that change as one drops to 0, the other reaches its max. As the other one drops to 0, the first one reaches its max. And that, in a very, very brief nutshell, is the kinematics and energy associated with simple harmonic motion.